Hello, welcome to another module in this massive open online course on estimation for wireless communication systems. So currently we are looking at frequency domain equalization, or what is abbreviated as FDE, alright. So in the previous module we have looked at the theory of FDE, which is frequency, which is frequency domain equalization, FDE, right? This is FDE, and this is basically previously this is basically an alternative to what we have seen previously, that is your zero forcing equalizer, which is a time domain equalization technique. So previously we have also seen the zero forcing equalizer, and this you can think of the zero forcing equalizer as basically a time domain equalizer, yeah, and that is also what we have said in the time domain equalizer, or basically TDE. And the disadvantage of time domain equalization is that we said it has matrix inversion. It involves, remember, zero forcing equalizer involves matrix inversion. Therefore, it has the time domain equalizer has a high computational complexity. It has a high computational complexity. On the other hand, when you look at frequency domain equalizer, frequency domain equalization is done in the frequency domain, as the name implies, and as we had seen in the previous module where we described the scheme, it involves a simple computation in the frequency domain, where basically you compute the estimate of the coefficient capital X hat L on each subcarrier L. Alright. So basically it does not involve any matrix inversion, and therefore it has a very low complexity, which means it can be implemented efficiently. So to summarize, FDE, again, although you have seen it explicitly in the previous module where we have derived or described this technique, FDE, which is basically does not involve matrix inversion, that is inverting, that is computing the inverse of a matrix, and hence frequency domain equalization is very efficient. Therefore, it is very efficient in the sense it has a low complexity, it has a low computational, it has a low computational complexity. It has a low computational complexity. Okay. For instance, let us now, in this module what we are going to do is basically let us look at an example to understand this frequency domain equalization better. Alright. So in the previous module we have described the technique. In this module, similar to the past several times we have discussed such schemes, let us do an example to understand how this technique works. Okay. So what we are going to do in this module is we are going to do an example for FDE, or basically your frequency domain equalization. Okay. So in frequency domain equalization, what we said is x0, x1, x2, x3. Again, let us consider a system with n equal to 4 subcarriers. Okay. Just to consider a simple system, although it can be extended very easily to a system with a higher number of subcarriers. Just to illustrate, for the purpose of an example, let us consider a system with n equal to 4 subcarriers. We said this small x0, small x1, small x2, small x3, these are the time domain symbols, these are not the samples, and that is something important to remember. It is an important difference in comparison to OFDM. Time domain whereas in OFDM we are taking the symbols, loading them onto the subcarriers, performing the IFFT and transmitting them in the time domain, transmitting the samples in the time domain. In FDE we are not doing any IFFT at the transmitter, we are simply taking the time domain symbols, adding a cyclic prefix and transmitting them, and that is the important aspect that one has to remember in FDE. Okay. So, let us take a simple example. Let this x0, which are the time domain symbols, these be given as 1 plus j, x1 equals 1 minus j, x2 equals minus 1 minus j, and x3 equals 1 minus j. These are your time domain symbols, correct? These are the time domain symbols. These are the, what are these? These are the time domain symbols. These are not, again, these are not, just to be explicit, these are not samples like OFDM. Okay, please remember that these are not the samples, and you can clearly see these are QPSK symbols. There is quadrature phase shift keying, that is, if you are familiar with communication, these are quadrature phase shift QPSK, that is quadrature phase shift keying. What is quadrature phase shift keying? Quadrature phase shift keying in the complex baseband is a constellation which has basically a real part and an imaginary part, and the real part can take either of two voltage levels, that is +1 or -1, and the imaginary part can also take either of two voltage level, +1 or -1. Therefore, you have 2 times 2, that is 4 symbols. One is 1 plus 1j, 1 minus j, -1 plus j, -1 minus j. So, these are the 4 symbols in QPSK, 4 possible symbols, out of which you draw the various symbols. So, what we are saying is small x0 is 1 plus j, small x1 is 1 minus j, small x2 is -1 minus j, small x3 is 1 minus j. These are the time domain symbols, alright. These are the time domain. In fact, to be more explicit, these are the time domain QPSK symbols, although one can choose any particular modulation, alright. That is not a restriction in this scheme. Okay. And now what we are going to do is, again, as we have said, we are going to take this time domain symbols, take these time domain symbols and add the cyclic prefix. So, I have x3, I take this x3 and I add this x3 over here. So, this is the, you are basically, and we have seen this also many times before. So, this is the cyclic prefix. So, in the sense that we are adding this cyclic prefix prior to transmission, it is similar to OFDM. Remember, in OFDM also we add the cyclic prefix. However, the important difference is, while in OFDM we take the IFFT of the symbols and transmit the samples, in FDE we take the symbols and directly transmit them after adding the cyclic prefix. Okay. So, now therefore, if I substitute this small x0, so what? So, small x0, what is your small x0? Small x0, so basically let me write this down. So, what is the transmitted? Your transmitted block is x3, x0, x1, x2, x3, and now let us substitute the values. X3 is 1 minus j, you can see from above that basically your x3 is 1 minus j, x0 is 1 plus j, x1 is 1 minus j, x2 is -1 minus j, and again x3 is basically your 1 minus j, and this is the block of transmitted symbols after addition of cyclic prefix. block of transmitted symbols after addition of the cyclic prefix. Okay. And now let us again consider the 2 tap ISI channel, that is YK. Remember, this is also something that we have considered many times before. Again we are restricting ourselves to 2 taps because to keep the example simple, although it can be readily extended to a scenario with many more taps, or in fact for any general number of taps L. Okay. So, we are considering, again to repeat it, with we are considering L equal to 2 taps. For the purpose of this example, let us specifically set H0 equal to 1, H1 equal to 0.5, which basically implies your Yk equals H0 is 1. So, it is simply xk plus 0.5 times xk minus 1 plus Vk. This is your 2 tap ISI channel. Okay. So, this is basically your Yk equals xk plus 0.5 xk minus 1 plus Vk. This is basically your L equal to 2 tap ISI channel, or ISI stands for intersymbol interference. L equal to 2 tap ISI channel, where your ISI stands for intersymbol interference. Just being a little explicit over here, intersymbol interference. Okay. So, we have Yk equals xk plus 0.5 xk minus 1 plus Vk, where Vk is of course the noise sample, Yk is the received kth output symbol, the small Yk is the received kth output symbol in the time domain. Alright. All the small quantities, the small letters basically represent the time domain quantities, the capital letters represent the frequency domain quantities. Alright. This is the notation that we have been following all throughout this course, in fact for the previous modules also, so as to keep the notation clear. Alright. This is the same thing we did in OFDM, and we are once again doing it in frequency domain equalization. So, small y is the time domain received output symbol, small x is the time domain transmitted symbol, small v is the time domain noise samples. And now when I transmit the cyclic prefix added symbols, we know that the channel operation, basically the linear convolution, becomes a circular convolution because of the addition of the cyclic prefix. Therefore, the output y can be represented as H circularly convolved with x plus v, where the circular convolution rather than linear, it is circular convolution, because, and that is important to keep in mind, because of addition of the cyclic prefix, this circular convolution has, this linear convolution has become a circular convolution, correct. And therefore, in the frequency domain, or basically after your FFT after the FFT at the receiver, this is basically given as, now you can see this is basically given as y of L equals circular convolution becomes multiplication XL plus VL, and therefore, this YL is the output coefficient across your Lth subcarrier, HL is the channel coefficient across Lth subcarrier, this is the channel coefficient across Lth subcarrier, a capital HL this is the symbol across the Lth subcarrier. And this is the noise sample across the Lth subcarrier. Now, let the output symbols, since we are considering an example, let the output symbols in time domain let the output symbols in time domain be y0 equals, let us say y0 equals 1, y1 equals half, y2 equals half, and y3 equals 1. These are your output symbols in the time domain. These are the output symbols in the time domain. Okay, these are the small y's. All right. Now, to calculate the corresponding outputs in the frequency domain, remember we have to take the FFT of these time domain symbols. All right. So, the capital Y's are given by the FFT of the small y's, which means I have to take the n equal to 4 point FFT. So, the symbols across the subcarriers YL, the symbols across the subcarriers YL are given as, well, we can write the expression for that, YL equals, well, this is simply the FFT of the, this is k equals 0 to n minus 1 yk e power minus j 2 pi k L by n, and this is the expression for a general FFT of order of length n. So, now we have to set n equal to 4, which is the number of subcarriers or frequency points in our system, which is equal to summation k equal to 0 to n minus 1, that is 3 yk e power minus j 2 pi k L by 4, which is equal to summation k equal to 0 to 3 yk e power minus j pi by 2 k L. Okay. These are the symbols across the symbol across subcarrier L or symbol at Lth FFT point, or the sample, let us put it the sample, this is in the FFT domain. So, let us say this is the output sample. Output sample across the Lth FFT point. These are the, for instance, yk is the kth output symbol in the time domain. Small yk is the kth output symbol in the time domain. So, small y's are the output symbols in the time domain, capital Y's are the output samples in the frequency domain. You take the FFT of the small y's and what you will get is the output, that is you will get the capital Y's, which are the output samples in the frequency domain across the various FFT points. Okay. And now, what we have is, we have already calculated this FFT before. So, I am not going to repeat that, y0, y1, y2, y3, okay, which are basically 1, half, half, 1, and we take the n equal to 4 point FFT. This is something that we already seen in the context of OFDM, n equal to 4 point FFT, I am sorry, not IFFT, n equal to 4 point FFT of the received output samples as I am just going to write as calculated previously. And we have calculated this in the previous modules, and this you can see is given as your capital Y0, your capital Y1, your capital Y2, capital Y3, which are basically 3 half plus half j, 0 and half minus half j. Just to be a little bit more explicit, let me write down y0 equals 3, y1 equals half, that is capital Y1, which is the output sample across the subcarrier or the first FFT point is half plus half j, y2 equals 0, y3 equals half minus half j. These are the outputs across the as we have already written over here, these are the output samples across the various FFT points or the output samples across the subcarriers. These are in the frequency domain, that is important to remember. The capital Y's are in the outputs in the these are the outputs in the frequency domain, that is something important to remember. Okay. Now, what do we need? We also need, remember that is the other thing that we need to compute the estimates of across the subcarriers. We also need these capital HLs. Now, let me go all the way back here and circle this. So, we need these HLs, which are basically, what are these capital HLs? If you remember, the capital HLs are basically the coefficients, the channel coefficients across the various subcarriers, and these are calculated by the 0 padded FFT of the channel taps in the time domain. All right, I would like to remind you of that. So, you take your 0 padded channel taps, that is H0, H1, pad them with zeros, that is n minus L zeros, you have L taps, which means you are going to have n minus L zeros for a general scenario. In this case, n equal to 2, L equal to 2, so you have 2 taps, and n minus L, n equal to 4, so you have 2 zeros, all right, and you take the 0 padded FFT, n equal to 4 point FFT, and just to keep in mind that this is the 0 padded FFT, and what you get are the channel coefficients across the, what are these? These are the channel coefficients across the subcarriers. Now, how do we get this? Therefore, if I write the expression for HL, I can write HL equals summation k equal to 0 to n minus 1, the time domain channel taps times e power j minus j 2 pi k L divided by n, substitute n is equal to 4, let me write this explicitly, substitute n equal to 4, and therefore, we have h of L equals k equal to 0 to 3 j 2 pi k L divided by 4, which is equal to k equal to 0 to 3 HL e power minus j pi by 2 KL. In fact, you can write explicitly, because although we are taking the summation from k equal to 0 to 3, it is a 0 padded FFT, there are only 2 channel taps. So, I can write k equal to 0 to 1 in fact, yeah, and that is something that you can remember because this is a 0 padded FFT. Why? Because this is 0 padded FFT and H2. So, we have H0 and H1 and H2 comma H3 are really speaking 0. So, let us channel taps. One way to think about this 0 padded FFT is to basically say that only H0, small h0 and small h1 are non-zero, while small h2 and small h3, that is the second and third channel taps, are 0. Okay, that is the same thing. Okay. Now, let us compute the FFT. Now, we know, and we have already done this also before, but let us just do this for the sake of completeness. We know that the channel tap h0 equal to 1, h1 equals 0.5. Therefore, capital H0, that is the 0th FFT point, this is equal to H0 plus H1 equals 1 plus half equals 3 by 2, H1 equals H0 plus the capital H1 equals small h0 plus small h1 e power minus j pi by 2, which is 1 plus half into minus j equals 1 minus half j. Capital H2, that is the channel coefficient across the second FFT point or second subcarrier, equals H0 plus H1 e power minus j pi equals basically 1 minus half equals half, and capital H3 is basically your capital H3 is the channel coefficient across the third FFT point or third subcarrier. This is small h0 plus small h1 into e power minus j 3 pi by 2 equals 1 plus half j, and therefore, now just writing all these things explicitly, once again you have small h0 equals 3 by 2, capital H0 equals 3 by 2, capital H1 equals 1 minus half j, capital H2 equals half, capital H3 equals 1 plus half j. Okay. So, these are the channel taps, these are the your channel coefficients So, these are the channel coefficients across the various subcarriers. Okay. So, we have the capital Hs. Okay. And now, what we have to do is basically, now if you realize what we have in the frequency domain across the Lth subcarrier, we have YL equals HL times XL plus VL, and we have to compute the estimate of the coefficient across the Lth subcarrier, right. That is what we do in FD, that is estimate of XL across Lth subcarrier, and that is denoted by your capital X hat of, that is denoted by capital X hat of L, and remember capital X hat of L equals Y of L divided by H of L. This is how we compute the estimate of the, this is how we compute the estimate of X of L across the Lth subcarrier, that is X of L, which is the FFT coefficient, X of L, which is the Lth FFT coefficient of the transmitted time domain symbols, the small x's, x, small x0, small x1, small x2, small x3. Okay. So, this we will compute in the next module and also compute the subsequent. So, these capital XLs are estimates in the frequency domain, then you have to perform, remember, the IFFT to compute the corresponding estimates of the transmitted symbols in the time domain. Okay. So, these two steps we will do in the subsequent module. So, what we have done in this thing is basically we are considering FDE, which is frequency domain equalization. We are demonstrating a simple example for frequency domain equalization. We are considering a block of transmitted QPSK symbols. We are considering an n equal to 4 subcarrier system. We are considering the QPSK symbol small x0, small x1, small x2, small x3. We have demonstrated what the cyclic prefix added block of transmitted symbols is, okay, corresponding received output samples, the FFT of the samples, FFT of the 0 padded channel taps. Okay. Now, in the next module we have to talk about what are the estimates of the capital Xs, that is the coefficient or the sample, the FFT coefficients in the frequency domain, and finally perform the IFFT to get the estimates of the symbols in the time domain. Okay. This we will do in the subsequent module. Thank you very much.